So let me introduce our speaker. So we are really happy to have Berfin Şimşek back, I should say, in our seminar series. So Berfin was a undergraduate student here in Koç University with double major degrees from electrical engineering and mathematics. And then she joined EPFL, where she did her PhD under the supervision of Clement Ongler and Wolfram Gessner. And she recently graduated. And she's currently a faculty fellow at NYU Center for Data Science. And she's also a guest lecturer at Flatiron Institute Center for Computational Mathematics. And during her PhD, she also had an internship at Meta AI, and she's mostly working on the theoretical machine learning. So she's at the forefront of theoretical research regarding how neural networks work and why they work and so on. So we will be really happy to hear from you, Berfin. Thanks for joining our seminar series. Thank you.
Well, thanks a lot for the great introduction. I'm also happy to be here, and well, I'll show you some results from my PhD. Well, the results that I worked on the most, and maybe I like the most actually. So I'm really happy to hear your feedback, and feel free to interrupt at any time. Okay, let me get started. And I'm afraid it might be a little bit technical, so I'd rather take more time at the beginning. So please do feel free to interrupt at the beginning, and I can drop the final slides. It's okay. So I'm going to talk about finite-width neural networks today, and a landscape complexity analysis. So for those who are not in the field, this finite-width expression might sound weird, but in the recent years, a lot of focus was on the infinite-width neural networks, where the dynamics simplify, and it is, while the loss landscape is effectively convex, and this was like, it was an easier, like, or tractable regime where like it is possible to prove some convergence guarantees. And there's been some progress on this, like with mean field limit techniques and neural tangent kernel techniques. But that's not what I'm going to focus today. So finite width goes to say, like, as opposed to the infinite width limits, I'm going to discuss finite width neural networks, where the loss landscape is much more complex, and we will try to develop a method to try to understand this regime of neural networks. So let me talk about width scaling in neural networks. And a key thing for us is overparameterization. So so it's a really quick field. When I started my PhD, all neural networks were overparameterized, like ResNets with 16 to 18 layers, and we were able to learn ImageNet with ResNets. And it was like there were many more parameters than needed to fit the training data. And by that, I mean, like, I'm plotting the training data over here. So these dots are the input-output pairs, and a neural network is a 1D function in this case, and it is shown as a blue curve. And there's another data set here, and here the neural network is a little bit smoother, and this is usually the picture in the neural tangent kernel regime for infinitely wide networks. But when we have a finitely many hyperplanes or neurons, we see more these kind of shapes. But this is to say, like, okay, overparameterization is the, we kind of assume, like, in the theory community that modern neural networks are like operating in the overparameterized regime because they are able to reach a zero training loss solution. And so they have a lot more parameters than needed. Even if the training data is noisy, they prefer to fit on the training data, and they can generalize well. So I want to understand, like, this regime. And I'm going to talk about our ICML paper from 2021, Geometry of the Loss Landscape for Overparameterized Neural Networks from the symmetry point of view. And if we have time, we recently applied this theory for a model identification problem. And this preprint is on archive now. So if you have time, I want to show you this application. And I will also like discuss some results that is only in my thesis. So that is a theory of finite-width neural networks, generalization scaling laws, and the loss landscape. And this work was in collaboration with my supervisors, Wolfram and Clement. And Johanni is a senior researcher in Wolfram's lab, and we've been working together on this line of work since 5 years. And there's Arthur, Francois, Francesco, Flavio, and Amir, who I've also collaborated with. Okay, so a little bit more on overparameterization. So before we talk about the theory, what does it mean in practice? So here in a very simple setup, this is a picture from Neishagur, 2017. So he takes the MNIST training data set, and he's training a one hidden layer MLP onto this data set. And we see here with already, okay, I'm not able to put my cursor on the plot. Okay, it's okay. Already with 32 hidden neurons, he's able to achieve an effectively zero training error. So we see on the blue dot. And as he overparameterizes further, so he could use more neurons. He fitted already the training error, like the training data set, but he can use more neurons. And we see that the test error goes further down as the model is larger. But we are going to be interested in the training error for today. And here is another setting with a shallow neural network. So here he's fitting on the CFAR10 data set with, I don't know, like 64 hidden units already. The model is learning a zero loss solution. And then what happens then when he adds more neurons? It was already enough to use a certain number of neurons. So this is the phenomena that I'm going to model today. And here, like how I read this plot. Huh? Okay, no questions. Here, how I read this plot is like in the first case, when there's 32 neurons, like the test error is not so good because the network converges to a bad minimum. But if we overparameterize further, now the network is going to find a good minimum, so the test error is good. And I want to understand this emergence of bad minimum when the network is not that large. Okay, so now let's look at a more toy setting where we can understand things more like in detail. So we created this toy functions. So here the target function is generated by two hyperplanes that we are plotting with a red dashed line. And so this is the target function that we are going to try to learn with a neural network. But we are like putting this hyperplane with some random angles. So we can generate more target functions. And this is what we played with in our archive preprint. So this is a target function generated by two neurons. So it has complexity 2. K is equal to 2. So now I'm fitting a 2 neuron student network on this. So there is enough expressivity, but does it learn the function? So we see, so each row here represents another target function. And we see for a certain fraction of initializations, the student is converging to a zero loss solution. So that's dark blue dot. And for the other seeds, it is getting stuck at a bad local minimum. So that's the yellow dots here. So the loss is 10. But now if I overparameterize it with 4 student neurons, now there's a larger fraction of seeds converging to a zero loss solution. Okay, if we further overparameterize, with 16 neurons, almost all seeds converge to a zero loss solution for all the teachers that we've generated. And so here at the first setting, I'm going to consider it as a no overparameterization. And then there's a factor to overparameterization, factor 4, 3, 4. And then in the limit, there's going to be the infinitely wide neural networks. So this is the well-studied regime in the literature. But we are going to, we try to understand what happens at the onset of overparameterization. And it's a similar picture, like if we generated a target function with 4 hyperplanes, K is equal to 4, we can train the pseudo networks again, and we see a similar qualitative behavior. And more specifically, the questions today is why is it hard to optimize without overparameterization? And what is the benefit of overparameterizing? And this is like the golden question. How much overparameterization do we need? So this is a really problem-specific thing. So depending on the data distribution, depending on the position of the hyperplanes or the true function, I think it depends on these parameters that how much overparameterization we should need. But I'm looking for a rule of thumb. So if I didn't assume anything on the input distribution, anything on the target function, can I have something in mind? And I'm going to use only network symmetries to find the rule of thumb for this. And in this picture, factor 4 seems to be good for this model. And okay, the approach today is going to be symmetries. So we are like looking at a non-convex loss landscape. And so we need some help from literature. So there are the complex loss landscapes, like spherical spin glasses, spike matrix tensor models. And these have been studied in literature, like for their own sake, because there's connections with physics and glassy systems from 2007, 2013, and so on. But in 2018 and 19, some people, like mostly physicists, try to understand neural networks through the lens of complex loss landscapes, and they made an analogy between these two systems. But I'm not going to claim that neural networks are like spin glasses or like another complex system, but I'm going to try to use the tools, well, not the tools, but the conceptual frameworks from complex loss landscapes and bring them for neural networks. So what happens for these loss landscapes is training dynamics are often intractable. And so it's not possible to prove convergence in general, but then one can count the number of critical points. Okay, so we have a similar situation for finite with neural networks. Maybe we can also count the number of critical points. But we have to be careful because there are symmetries for neural networks. So this is similar to dictionary learning, clustering, tensor decomposition. So there are multiple equivalent solutions. Here in the first picture, I'm showing a rotational symmetry. So there's a manifold of zero loss solutions. In the second picture, there are discrete points that are all the bottom of the loss landscape. And in the third picture, I'm showing you a particular kind of symmetry that is not at the bottom of the loss landscape, but it is a line of critical points, and we see like some settles on it, local minimum on it, and they are all at the same loss on the same line, but there is this curvature banding down and then further up kind of situation. But yeah, that is something I should write this year. Okay, so this is the outline today. So I want to first introduce the symmetry approach to landscape complexity. Okay, let's take a neural network. So that is represented by f theta. So input is d-dimensional and the output is one-dimensional in this setting, but in the paper it's more general. And the f theta x is a sum of n neurons. So it's AJ. Okay, I have also pictures of neural networks. AJ is the outgoing weight, so it's one-dimensional. And WJ is the incoming vector, it's d-dimensional. And a neural network is the sum of its neurons. And if I put all these parameters together into a parameter vector theta, it is the network parameters. And so there's a particular symmetry operation that happens for neural networks. So it's let's take a green neuron and split it into two pieces. So this is what I'm calling neuron splitting here. So specifically, we are taking a neuron W1A1 and copying W1 into two neurons and splitting the outgoing weight mu times A1 and 1 minus mu times A1. So these two neurons sum up to the same thing, same neuron for any value of mu. But what is surprising, if you don't write the gradient formula, is that this operation preserves criticality. That is, if the first neuron is a critical, if the first parameter is a critical point, and after neuron splitting, for any value of mu, we get a critical point as well. So this is the point where the gradient of the loss is 0. It could be the bottom of the loss landscape. It could be a saddle point, like a horse saddle. We could think about it. Or it could be a maximum. So they're all critical points. And this was known since 2000 by Bikumis and Amari. And there's a second symmetry operation. So that is, we can take one of the neurons. We can add a new group of neurons that I'm showing here by gray. So that's W prime. And I'm setting A prime in the second layer. And these two gray neurons add up to 0. So they cancel out each other. That doesn't change the network function. And this is going to be relevant for zero loss configurations, because this actually breaks criticality. So two symmetry operations that we are going to consider. Maybe I pause here for a moment if there's any questions.
Okay. I think, can you clarify what do you mean by preserving criticality exactly?
Yes, yes, thank you. So that is for, like, if the first parameter theta in the small network, I'm assuming that that is a critical point. So the gradient of the loss is 0. Now I'm adding a neuron to it with this operation. And the claim is that this new parameter is also a critical point of this larger network. Well, of the loss of the larger network. Yeah.
So you have this, I mean, you basically introduce a redundant neuron, right? Which is basically tied with the same W1 weight. And you are basically taking a convex combination of their outputs, I mean, the multiplied by A1. So that is in the training, during the so you are basically just looking at the loss landscape with W1 and A1 still. Those basically two neurons, green neurons, they have still constrained to have the same W weight, right? Is it? And A1 weight.
It is totally, it's a construction, and we don't know if the training dynamics visit these configurations. But so we're like, it is, what we will find is that this is a construction, but there is going to be a lot of like such critical, well, manifolds actually, because this is also a line of critical points. It is for any mu, it's a critical point. But anyway, we can, so there's going to be a lot of such manifolds, and that's going to like kind of squeeze the loss landscape in some way. And we want to understand this global loss landscape. So we will not discuss training dynamics actually. I mean, like, yeah. So it is a particular construction. So you got it right.
Thank you.
Okay. And more particularly, because so I'm assuming that there's a training distribution, and that is well, X is distributed with this probability P. And because I want to talk about the critical points, whether they are saddles or minimum. So I'm assuming that there is a well-defined Hessian, or that I need to assume C and sigma are twice differentiable. And I'm assuming that C is 0 if and only if Y hat and Y are equal to each other. And I'm assuming that there's a target function, like I was showing in the first picture. That is, so the function that we are approximating is generated by a neural network. That is what I'm writing here. And this neural network has K neurons. And this is also known as the teacher network. And so important definition is irreducible parameter. So I'm the concatenation of all these parameters is an irreducible parameter if the network function cannot be represented by a smaller network. So that is to say, this F star cannot be generated by a smaller network. K is the minimum, K is the minimal. So theta star here, for example, is an irreducible parameter. That's the assumption. And finally, this K is going to give me the complexity of the target. And if the network is smaller than k, it is underparameterized, and if it's larger, its width is larger than k, it is overparameterized. And in literature, k equals 1 is very well studied. So there's a phase retrieval problem where there's already complexity due to finite sampling. But this landscape is simple in the population loss limit, and that is consistent with some Beatty and Udeya's work. So in the population loss, when k is 1, the loss landscape is simple. But for k larger than 1, we will see that there is already complexity due to symmetries in the population loss limit. Okay, so I think I'll skip this part because so yeah, I wanted to discuss this the second order information of the critical points on one single line, but I think we can skip it. I mean, it is interesting on its own sake, but we can do the rest without that part. So I want to talk about the scaling laws of critical manifolds. So let's start from a width and network. And I'm using these buckets to represent the network as a sum of its neurons. And we are applying neuron splitting onto a neural network with m neurons. Okay, so there's a lot of ways to split. So here the green neuron is split 3 times, for example. And then the second symmetry is 0 neuron addition. So the question is, how many configurations are there from a set of n neurons onto a set of m neurons? So starting from n, mapping onto m. And we want to use each neuron at least for once. So let's say I'm using the first neuron k1 times, and neuron kn times, and they are filling m positions. And each neuron is used at least for once. That's why I have the second constraint. And for each such partition, there is permutation symmetry. So that I'm showing here with a multinomial over here. So it's m choose k1 to kn. And then I'm summing over the partitions. So this is the first way to write this scaling law, but we will have a better way to write it later on as well. And the second scaling law is the number of zero loss solutions. So that's now important. I'm starting from a network with k neurons and mapping onto m neurons. So I'm mapping the parameters of the teacher network onto an overparameterized network. So if I don't use any zero neurons that I'm showing here by gray, the number is equal to G, where the only allowed operation is neuron splitting. But then I could use I of the m neurons for zero neurons. So that's why I goes from 1 to m minus k. And I can choose the position of this I neuron. So that's m choose I. Then there's, for the rest of the neurons, I get the neuron splitting. And then there's the partitioning of these I neurons within zero neuron groups. So that gives us the span number. But maybe a better way to write this. So I want to focus on the first scaling law. And so we are going to discover a connection with the enumerative combinatorics when we write it in a better way. So this scaling law, we can write it, we can think about it as a mapping from a set of m elements onto another set of n things. So from larger set onto the small set. So now I'm doing the other way around. And then it's actually like this, the Stirling number of the second kind is the number of surjective functions from a large set onto the small set. So that gives us the mapping or the particular partition. And for each such thing, because there's permutation symmetry, there's an n factorial for coloring. So this is another way to write it. But once we get it, we see that this was actually like a popular or interesting question for some like top-notch combinatorics people. So this was discussed, asked by Tim Gowers and answered by Terence Tao. And it turns out like, so they were interested in the maximum of this distribution. And they were like, so if we actually plot this scaling law, the first one up, it increases first and decreases later. And they were like interested on the maximum, where does maximum kicks in. And they're like, there's a row, and it's like, it kicks in at 1/2 log2. And it fits with my simulations for the finite values of m. It already kicks in early on. So I want to discuss like what this means for neural networks. So I need a complexity measure. So that compares the scaling of the saddle manifolds at the loss, where the saddles are generated by k-1 neurons. So that's really low loss saddles versus the zero loss manifold, like the number of zero loss manifolds. So that is a number T. So K is a teacher width and M is larger than K, greater than or equal to. And so it turns out in the infinite width limit, this complexity goes to 0. So it's consistent with literature where like it's possible to prove convergence to zero loss solution. But if we don't overparameterize, or if you mildly overparameterize, then the complexity explodes. So it approaches to infinity for when K approaches to infinity as well. So really for complex data. And I can also plot this complexity value, and this I don't have a analytic result on this, but we see that it gradually decreases. So the more neurons we add, it really like gradually becomes nicer and nicer, the loss landscape. This is consistent, maybe like it gives an explanation for like why we are getting nicer performance with more neurons. And I can say one more thing for deep. So far, we were only discussing shallow neural networks with one hidden layer. But if the teacher network has 3 hidden layers and 4 neurons in each hidden layer, the student has 1 more neuron. Then we see that the student fails to converge for all fractions of initialization. So that is and this is like worse than the shallow case, because the complexity. So at every hidden layer, there is permutation symmetry. And it makes the loss landscape much more complex because these factors get exponentiated with the number of hidden layers. So when complexity is larger than 1, it blows up exponentially with depth. So that's the onset of overparameterization. But actually then on the, once the complexity is smaller than 1, the depth helps with training. So it's it really makes this complexity curve sharper. I mean, the depth makes it sharper. Okay, and this is maybe the most important slide, if you're still listening. So if we take a neural network with n neurons, so n is now smaller than k. So this is an underparameterized neural network, and I'm taking the minimum loss configuration. Because this is smaller than the target function, right? It can't fit a zero loss solution. I don't have enough neurons, so it achieves an epsilon and loss level. So with 1 neuron, there's a high loss. With 1 neuron, we don't learn anything nice. 2 neurons, we do a little bit better, so on. With k neurons, it is possible to learn perfectly and achieve zero loss. Okay. So those are the loss levels. And now I want to apply this scaling law for a non-overparameterized neural network. So this is the beginning is the non-overparameterized regime. And we saw this unimodal curve for the scaling law G. And here the circle shows the radius of the circle shows the number of configurations. And so there's first one mapping from 1 neuron onto m neurons. There's only one way to map. So it's one big manifold, but then it's kind of, it goes like 2 to the power m, 3 to the power m. So there's this exponential increase in the number of configurations, but then it shrinks down. And I'm claiming that this like kind of table lamp kind of shape is very bad for training, because this global loss landscape, so there are many more saddles than the zero loss configurations, and each saddle manifold is creating a pocket per basin of attraction. So there are a lot of basins of attractions, but only some of these are filled in by the global minimum manifolds, and the other pockets are empty. So they create like some other sort of local minimum. And that's what I'm suggesting with this picture. So it's extremely complex in this regime, the loss landscape. But now if you overparameterize by a small factor of 2 log 2, so we just, this splitting applies only until we reach the peak of this curve. And then the most numerous configurations are now the zero loss manifolds. So we don't get this, like the local minimum that I was describing from before, but there could be other critical points because I studied one particular sort of critical points, as Alper pointed out. But so we don't get that form of difficulty at least. So it's a nice property to have. So with further overparameterization, we get less complex loss landscape. And then if we take an infinite width limit, the complexity, remember that the complexity goes down to 0. That means the number of zero loss configurations, that is this green circle, well, the size of the green circle, is much larger than the competing number of saddle manifolds. That's the dark red over here. So there's infinitely more zero loss solutions than anything else, the other symmetry in these critical manifolds. And this is a regime where like there are a lot of like nice proof techniques we can apply, and it's nice to study. And how much overparameterization do we need? Going back to the first question, it's at least a factor of 2 log 2. So that's the rule of thumb that we take out from this analysis. Okay, any questions on this slide? I think this is the most important for this talk.
I have a question. So here in this regime, as we go towards the right, like, is it that we are finding global minimas with higher probability, or is this overparameterization also helping dynamics that we are able to escape saddle points?
Yeah, great question. So I can't answer this like with the on the theory level because my analysis is not that fine. So I think what is going on is it's helping with both. So there is a larger probability because there is of convergence because there are more zero loss solutions. But at the same time, this global shape of the loss landscape, like depending on how the shape is, it creates like more difficulties or less difficulties. So it does affect the dynamics in a very non-trivial way. So it also helps with dynamics as well. And that's consistent with the empirical results that I've been flashing. Does it answer the question? No?
Yeah, thanks.
Yeah. Okay, cool. Very good.
Berfin, maybe just for clarification, I'm a bit confused after the stage that you basically have a k-width original network, but you are looking at m-width basically network that you're going to train with the cost function, and you basically count m-width networks which are preserving the same critical points as the k-width network, is it? And then how do you reflect it to the number of saddles and number of Bayesian points, I guess. So you are basically looking at the ratio of them as far as I understood, right?
Yeah, the ratio is this complexity measure that I have on the top left part of the slide. So that is that is one measure. But I don't think it's the only thing that, because I'm trying to draw like some conclusions from these scaling laws, right? That's like what I want to do. And then I'm looking at 2 things actually. The first one is the ratio. So I can plot this number, and that's what I'm calling the complexity. But then I can actually, I want to understand like the global loss landscape. And that's what I'm doing with this plot or sketch.
Okay. Thank you very much.
And I wanted to talk about the second scaling law because I want to show a theorem. So now I want to give a more precise result. So far I talked about these constructions, but I want to convince you that I didn't make up these symmetries, and they're actually like the essential symmetries. And in what sense? So if I assume more things, that input distribution has full support, Then the activation function has no symmetries. So that is, I'm assuming that it's analytic. It doesn't cross zero, it's zero. And if I look at its derivatives at even values, it's zero. There are infinitely many non-zero. And same for the odd derivatives. So this last condition is to say the activation function is not odd, or to say it's not even, or to say it's not even plus linear, which is a ReLU is an even plus ReLU activation function, because we can write it as an absolute value plus a linear function. I don't allow those things, but it is not a fundamental problem of the proof. I just need to work a little bit more careful if I want to include other activation functions. And with these assumptions, I can say all zero loss parameters in overparameterized networks are identical to the teacher parameter up to neuron splitting and zero neuron addition. So these are exactly the two operations that I introduced. Okay, and there is whatever zero loss point is there in the loss landscape, it is in the union of the manifolds that I was describing before. So this gives the full picture for the bottom of the loss landscape. And then moreover, if I want to talk about the topology of this manifold, it is connected the set of zero loss points. And I can even show you some nice pictures. So I can take a teacher network with 2 neurons and the student with 3 neurons, and I can compute this number T. It has 12 manifolds. And then each manifold is connected in a certain way. If 2 manifolds intersect each other, so I show the manifolds as dots, and if they intersect, I draw an edge in between them. So we see this connectivity graph. And I can also plot it in, and the teacher has 3 neurons and the student has 4 neurons. There's 16 manifolds, and they are like, the topology works in this like a combination of these hexagonal shapes, and they have to wrap around each other. So it has to fit on a torus, it turns out. So we were able to give this more precise like description of the zero loss manifold, more than the connectivity. There's been a huge history to show that this zero loss manifolds are connected for overparameterized networks. And I'm giving a list of references here. And I think this is a very interesting question in general, like to study the full exact topology, because we have the analytic description of the parameters, but I don't know this connectivity graph like for all cases of overparameterization. And I think it's a fun and interesting question. And do I have time or?
Yes, we do. You do have time.
Berfin, can I ask a question quickly?
Yes, please.
In the previous slide, what do you mean by critical points being connected?
Yeah.
Sorry, the manifolds. I think there are manifolds being connected, right? But I got lost there.
Yes, thank you. So yes. So I mean, if 2 manifolds intersect each other, then I say they are connected.
Oh, I see. Okay. Thanks.
And yeah, each manifold is an affine subspace, and yeah, here it's like an abstract graph picture to keep track of this, how they are located together. But actually, in the first case, it looks like not a hexagon, but if it has 12 corners, like that polygon, like it looks like lines connected together, like in this kind of way. I mean, and I'm now projecting it on the 2 dimensions, but the weight space is much larger dimension, so these affine subspaces could rotate a little bit, but that's the idea.
Okay, thanks.
Okay, so I promised an application. So for the theory, so there is the expand on cluster algorithm for model identification. So I hope I convinced you by now that so if we have a certain number of parameters and we have a loss landscape, but this is if we didn't add extra neurons, it is hard to find the global optimum of this loss. So we don't know how to solve this reliably. So what we do, we expand or we overparameterize the neural network onto a larger network. So now this is a nicer optimization loss landscape. and we can find the global optimum of this larger parameter space. And then from this, and we are doing it for n seeds. That is why there's a cross n here. Then we are looking at all the neurons of all these networks, and we are like collecting these neurons and applying a hierarchical clustering algorithm to group the neurons together and get rid of the zero neuron groups that don't match across seeds. So we recover the global optimum of the original problem. Well, we hopefully recover. We don't have like theoretical guarantees for this because it's very hard, like, or maybe impossible to prove convergence for this finitely overparameterized regime. But we try this numerically, and for a teacher network with 4 neurons, so when rho is equal to 1, you see that this orange dots are hovering at, I don't know, 0.5 high loss level. So it doesn't converge to a zero loss solution. Then we overparameterize and we collect all these seeds. So each dot is a different seed, so it's a different random initialization. Then we collect all the neurons of all these seeds together and apply this hierarchical clustering algorithm. Then it gives us it gives us a zero loss solution. And we can do this for deep neural networks as well. But then we are not fully recovering the teacher network. So we get an extra hidden neuron in the first hidden layer. And then we managed to do this for MNIST as well. So, but there's a small overhead in the third hidden layer. Remember that the theorem for the zero loss manifold applied only for the infinite many data points or the population loss. And here, of course, like because we are coding this up, there is the effect of finite sampling. So we try to densely sample the input space, but there's already 4 input dimensions in the first picture. So it's there's going to be finite size effects. But despite that, the geometry that I was describing seems to be also here for this finite size input data situations. And so important thing is like it was actually like numerically it wasn't a very easy task to cluster the neurons, because unless we reach really low loss levels, they were like, even if the neurons are close, like functionally close together, the parameters, the vectors would be still farther away from each other. So it was important to go down to really low loss levels, and that's why Johanni implemented a package written in Julia to integrate out this gradient flow dynamics, and we relied on this package. Okay, to summarize, what we saw today, non-overparameterized neural networks are extremely non-convex, typically, and this complexity decreases with overparameterization. So a factor of 2 log 2 is very nice to have. It's not that large, it's 1.4. And then it ensures that the zero loss manifolds are the most numerous compared to the other symmetry-induced manifolds. And then we see like this static analysis affects the training dynamics as well, and we see some empirical signatures. And this is the global shape of the loss landscape that I'm sketching. So we describe the topology of the zero loss solutions. It's a connected union of affine subspaces, and we can draw the connectivity graph in some cases. And we can propose a neuron pruning method, expand and cluster, to eliminate the redundant neurons. Thanks a lot for your attention, and I can take further questions.
Thanks a lot, Berfin. Thank you. I do have a question. If if we have regularization terms, does that help in terms of this loss landscape characterization? Like, can we get like better behavior in terms of and for your numerical experiments where you started with m equal to k and so on, is it sensitive to also like choices of whether you are using SGD or Adam rule or something like that, the algorithms that you choose? So that are my questions. Berfin, your mic is off. Yes.
I'm sorry. Yeah, for the regularization question, I got it during my private defense in front of the jury, and I didn't have a great answer. And I'm afraid I still no, but it's for the global minimum manifold. Actually, like there's this affine subspaces of zero loss manifolds, and if we put an L1 loss, for example, so it will, like you were saying, it will be like a convex hull. So it'll be like a line segmenter like this, or if it's very higher dimensional, the convex hull of this polygon thing. And I didn't. Intuitively, it looks like this. And for the settled manifolds, it could be even more interesting because maybe it could like remove this escape parts of the lines. So there, I skipped this slide, but well, sometimes these what I call the settled manifolds are not like only made up settles. Sometimes there's a segments of minimum, and then it connects to settles. And if we added an L1, it could have been like local minimum and upwards. So it could remove this escape directions. So in that sense, maybe it's yeah, this is for L1, but maybe it's I don't know. So there are a lot of interesting questions there. That's for sure.
Quick question: when you say L1, do you mean like changing the, for example, MSE loss to L1 loss, or enforcing an L1 regularization on the weights?
I mean, adding an L1 regularization.
Okay.
If I change, I didn't assume anything on the original loss function, right? So it would be the same description if I change the loss. I just assume this thing that it is zero. What? That is zero if the target and the label matches. Yeah, so that's that. And for the optimizers, so I mean, for the numerics, we integrated out the dynamical equation. So it's an approximation of gradient flow. But this loss landscape the static description is there. So my guess is that if we change the optimizers, we would see still this difficulty. Like I don't expect that this using Adam is gonna save us from this complexity. So it is a strong like effect, I think. And it's actually for the first clause that it's not our experiments, but the denomination works. I think he has either Adam or SGD here. So we see still like this overparameterization at the beginning helps. So yeah.
Thank you, Berfin.
Can I ask if there's no other questions? So the second theorem that you showed, you proved, right, which says that all the zero loss minima actually fall into the category that you described in the first part, right? The overparameterization schemes that you suggested, right? So do I understand it correctly? Can be basically produced through those procedures. So the initial conditions that you imposed on the loss function, how general are they? I mean, are you really? I mean, does it cover pretty much, the typical loss functions that people use?
Yeah, it is yeah. So logistic loss is fine. Square loss is fine, but for the theorem, there are some other non-realistic things. I can tell you, like I needed one output node for the theorem, and unless there are 10 classes, right? But maybe, yeah, for empirically, still we could apply the same algorithm, and we found the same structure. But so this for the theorem, I'm less sure how to generalize it. But I think the big assumption is the population loss. So I'm assuming that there's an input distribution, and I'm like, how should I? There is the training loss. and generalization loss, right? But I'm collapsing these two on top of each other.
Okay.
And actually, I'm describing the bottom of the generalization loss landscape. But then there's finite sampling here, and still it's because the finite training error is kind of a perturbation of the population loss if there's a lot of training data sets, training data points. And then it's it's kind of somehow maybe robust when we have a lot of data points. This is the more like non-realistic thing, because normally we know. So in my framework, like all zero loss solutions are identical in the function space. Right. But for neural networks, we know like there are some bad minimizers.
I see. Okay. So you mean identical because they follow from the symmetry procedures that you defined?
Yeah.
Okay.
Yeah, I mean, or maybe like just to defend the once there's a teacher network and infinitely, or like I'm studying the population loss, it turns out all zero loss solutions are identical in the function space. So this is kind of the limit of the practice, in the infinite data limit of the practice. So maybe it's good to think. So there was this line of work studying infinite width, and I'm studying the infinite training data.
Okay. Thank you.
A quick question. As far as I know, you exclude Rayleigh-like activations from this work, but from an intuitive point of view, or like if you've done any empirical studies on this, how does this complexity measure look like for Rayleigh-like activations, where we also have this scaling invariances?
Yeah, great question. So I think the scaling invariance is fine, because what it does, it changes the geometry of this manifold. So far we had affine subspaces, but if we had scaling, it becomes like an hyperbola. And then you get an extra degree of freedom. So it gives you, like, the manifold grows one more dimension larger. So it changes the geometry of the manifold, but I don't think it changes the number. The scaling invariance doesn't change the number. But there is another thing with ReLU, that it's what we call the symmetry class is different. So it is, as I said, it's an absolute value plus linear. So it's an even plus linear. It's in this class. So it is the same for soft class, for example. And then like the numbers change for this class, because now I'm allowed to flip the sign of the incoming vector. So I can, if it was even, let's forget about the linear. If it was an even activation, I can just flip the sign of the first layer, and it's the same function. So it's another symmetry, and that changes the number. So, and I don't have the number calculations for this section, but it's something really interesting.
And like in terms of that complexity, for example, are they I don't know, like easier to find, like, or the global minimum manifold, is it like larger per se compared to a sigma, for example?
Yeah, great question. So it's because there's more symmetries, there's going to be, the manifold is going to be, the zero loss manifold is going to be larger, but then the settled manifolds are also going to be larger. So now the question is, like, which one scales faster? And, so this I don't know. Actually, we have some. Are we on? Okay, I could tell you a preliminary result, but if you are not on, if you are not recorded.
Just a second, Berfin. Neslihan Hanım, can we stop recording?
And great question.
Bye.
Okay. Thank you. Bye.
Bye.
Thanks.